All right, so say we're given a problem like this, right? Leak code number 70, climbing stairs. You're climbing up a staircase, and each time you can either climb 1 or 2 steps. How many distinct ways can you reach the top of the stairs? Say we have this example right here where the number of stairs is equal to 3, and here's a little visual right now. So our output would be 3 in this case because there's 3 different ways to get to the top of the stairs. You can either go 1 by 1, which is one option. You can go up 2 and then 1, which is another option. Or you can go up 1, then 2, which is how we get our 3, right? In our example, if the number of stairs was 8, our output would be 34, right? So we can actually solve this problem recursively. So this can be seen through a tree diagram. So the tree diagram would look something like this, right? Say we had DFS. We're going to run def first search on this function recursively. So we had DFS event, right? We're prompted with 2 options, 1 or 2. We can either take 1 step or 2 steps down. So if we take 1 step where we subtract n minus 1, then we would have DFS of n minus 1 here. Or we could take the other step, which is n minus 2, and we get DFS of n minus 2. And then for each of these children, we also run the recursive call of DFS n minus 1 and DFS of n minus 2. And same thing for this child. Right? And we keep doing this pattern until we reach our base case. And in this case, our base case would be if DFS reaches 0 or DFS reaches 1. Because if we have a staircase of 1, like this, there's only one way to reach the top right here. And that's just to climb up 1 stair. Right? And if DFS of 0, which means there's no stairs at all, we're already at the top. So there's 0 ways to get to there, right? So this, say we reach the bottom and it's DFS of 1, and say we reached another base case, which would be DFS of 0 for each child. 1, DFS of 0. Just like that, this would compute all the combinations for this, and it will do that by kind of backtracking its way back up to the top. Right, once we hit this base case right here, we're gonna return 1, which means we found 1 combination. And so if it hits 0 or 1, this right here will backtrack up, giving this parent function 1. And this would backtrack up, giving this 1, and then it would add it, giving us 2. And then this parent would take this 2 back up to its parent, and it would store this 2 here, while this branch is doing the exact same thing. This will both return 1 and then add them up to here, so we have a 2 here, and then take this 2 and backtrack it up to its parent, which will have 2, and then add them until we get the 4 right here. And that 4 will backtrack up to here, which would be waiting on this side to finish exactly what we just did here, for us to get our final answer of combination. So it would be 4 plus whatever this would be, which would also probably 4. So our different combination would be 8 in this case if n was whatever number of iterations the length of this tree was. Right, so this whole combination can be thought of by this right here. It's going to be the sum of DFS at n minus 1 and the DFS at n minus 2, because we only have 2 different options given to us. We can either move 1 or 2 steps, right? So this solution right here would have a time complexity of O of 2 to the nth power. And why it has that time complexity is because, say we're given n right here, the length of the tree would be n. And on each recursive call, we make 2 more recursive calls. So n is being doubled every single time we make a recursive call. Notice how we have 1, then we have 2, and then we have 4, then we have 8. And if this would kept going, we would have 16, 32, 64, 128, 256, all the way down until we reach this base case right here. Right, so that's why it's O of 2 to the nth power, which is an exponential time complexity and something we want to avoid when we're using recursive functions like this. So in order to optimize this, we're going to have to use memoization. Now memoization, the whole idea around memoization is to cut unneeded branches, right? So notice how we repeat n minus 1, n minus 1, n minus 2, n minus 2. We repeat the same steps over and over again, making this exponential, right? So memoization, what it does is once you go down the tree and you return the values back up to its parent, it stores those values in, say, well, you can store it in whatever you want. Some people store it in an array, you can store it in a map, either way, but it stores those values. So every time we see DFS of n minus 1, say over here, where we already calculated DFS of n minus 1, we don't need to calculate it again. We can just return that value right off the map or right off the index array. But it is better to use an array when dealing with this, because if you use an unordered map, the average complexity is constant, but that's only on average. On its worst case scenario, it is logarithmic. So, but with an array, you're guaranteed it will be constant time. So I would recommend to use an array here, right? So if we implemented DFS memoization to this DFS function right now, what would happen is we would go down here and then save all the data. So n minus 1 gets saved, n minus 1 here, and then n minus 2 gets saved. So once we backtrack all the way up to our parent function, we don't even have to calculate this branch anymore because we already did right here, right? Because notice how DFS of n minus 2 has 2 branches, 0 and 1. And this 2 this 2 right here has 0 and 1. So these branches are exactly the same. So we're repeating steps we don't need. And so this whole entire branch right here can get cut off. Now, it might not look like a lot. We're only cutting off 1 branch, which is connected to 2 childs. But imagine if this n was like 500. This tree would be absolutely huge. It would be 2 to the 500th power. And that's how many recursion calls there would be. But yeah, that cutting off this branch could cut off a whole hundreds of thousands of unneeded calculated branches when we do that, making our time complexity from exponential to linear, O of 2 to the nth power, which would just get simplified down to O of n. And it does that because since we cut off this branch right here, all of these have 1 child because there's 2 options. So this right here is a linear path, and each linear path has 1 child extending off of it, making it O of 2n here.